Well, welcome to the first part of our notes on the periodic table. So we're going to go into a little bit more detail about the periodic table. And of course, you've seen a lot of the important things about it already in our atomic structure unit. The first question I want to get to, and this is what the opening activity was about, is why is the periodic table arranged the way that it is? It is a little unusual, of course. I mean, you can see not all the columns start at the same place. There's this little gap here, and then there's this big gap here above columns 3 through 12. So, what is that all about? And it has to do with patterns, periodic or regularly occurring patterns. So the best example I could give you would be the patterns that we see if we look at all the days in a month. So I listed the days in the month of this month, or next month actually, when I'm recording this. And if you notice, every 7 days, a pattern repeats itself. See how we start Friday, Saturday, Sunday, and then further down here, Friday, Saturday, Sunday. Well, what if we decided every time that pattern got introduced again, that we would just break it off and start a new line? And of course, we could do this on a Friday, but we could do it any day of the week. Well, what do we get when we do that? We get the very familiar calendar, of course. This is what a calendar is. So they start not on Fridays, but on Sundays in most calendars, or you could start on a Monday or any day you wanted to. Maybe you like weekends, and so you want to start on Friday. But that's why we break these into 7 chunks, because that's the repeating pattern. Well, what about a different pattern? For example, what if it's just a list of numbers? I've listed the numbers 1 through 30-some here. Well, what pattern do you see there? Well, I notice that these are all single digits. Okay, so if I stop here, notice I have 0 here starting again. And then I go through 9, and I could stop there and start over again. And then every time I hit a 0 in the ones place, I could just start over again. And so if we have an arrangement like that and we put it on a piece of paper, this is pretty much what we get, right? So what's nice about this is not only are there patterns within each row. For example, the first row doesn't have a tens place. The second row has a 1 in the tens place, and then a 2, and then a 3. But there's also patterns within the columns. So the first column starts with 0, or ends with 0. This next column over ends with a 1. The next column over, the last digit's a 2, and a 3, and a 4, all the way over here to 9s. That's a pretty logical way to arrange those numbers, don't you think? And so this is exactly why Mendeleev arranged the periodic table the way that he did. So it's not just the numbers either. It's really more broadly the properties. So you can write here as I write. Remember, if I ever write too fast, you just pause it or slow down the video and you can catch up with me. So the properties of elements, and these are the 118 elements that we're talking about here, they follow patterns. Within the horizontal periods, remember that's another name for the rows, and the vertical groups. And groups is the name that we use for the vertical columns. Watch the spelling of columns. It's a little unusual, don't you think? So we'll see a little bit later in this chapter that if we look at, for example, the very first column, we call that group 1. They also have another special name that we don't need to worry about now. They all have very similar properties. In fact, some of them are explosive. That's a property that they share. Hydrogen is explosive. Some of these will even explode if you put it in water, of all things. And we have this group over here, group 18. They are particularly known for being unreactive. They don't do anything with any other chemical. Okay, so that's just an example of some of the properties that we look at when we decide how to arrange these things. Okay, let's go on to the next page. So we're going to do what's probably going to be a lot of review here. Just remembering what we know about an atom of an element. Remember, 118 elements. The smallest piece of an element is known as an atom. It's made up of subatomic particles, protons, neutrons, and electrons. Depending on how many of each of them you have, that makes a particular atom, and we give it a name. We call that the name of the element. Okay, so what can we know just based on where it is on the periodic table? This is a lot of review. So the number of protons, we just have to look for its atomic number. We did that a lot in the last chapter. Okay, the atomic number on this chart here is the very topmost number. It's a whole number. It's also the number that is in order as we go left to right across the table. How about the number of electrons? So if it is a neutral atom, it's also equal to the atomic number. Now the electrons can come and go. So I'm talking in particular about a neutral atom. That's an atom that hasn't lost any or gained any of its electrons. Sort of the normal number if you want to think of that. Okay, I emphasized this in the last unit. The number of neutrons cannot, I will capitalize this, cannot be found on the periodic table. That's because for almost every element, there are multiple versions of the atom. Some have more neutrons than others. They all have to have the same number of protons if they're a particular element, but they don't have to have the same number of neutrons. I use the example of hydrogen. There's hydrogen with no neutrons at all. There's some hydrogen with one neutron and some hydrogen with two neutrons. Okay, the number of any energy levels that have electrons. Okay, so the electrons exist in these, we draw them like orbits. We call them energy levels. You'll also hear them called shells sometimes. So those electrons are in the shells. Well, how many energy levels do the electrons take up? That's equal to the period number 1 through 7. At the time of this recording, there are only 7 known periods. Okay, so the periods are the numbers along here that tell you which horizontal row that you're in. Okay, so remember this is the row for the number of energy levels. Okay, circles, if you were to draw all the electrons in, you would draw circles around the nucleus like an orbit of a planet around a sun. Okay, how about the number of valence electrons? Valence also means the outermost electron. So when we're on that outermost energy level, how many electrons are there? This is equal to the group that you're in, okay, or the column. Now it's not equal to the number, but it's related to the number. So if you are in groups 1 and 2, you will have 1 outer electron or you'll have 2. And then we skip all of these up through group 12 and we start again at 13. Everything in group 13 has 3 outer electrons. And then as we go over from there, we get up to finally the biggest number, which is 8 outer electrons for all of the elements in group 18. And the average mass of an atom, okay? This is also found on the periodic table. It's like the decimal number. On your periodic table, you'll see it there. I've emphasized you cannot use that to find the mass number of a particular atom because there are different kinds of atoms, but you can use it for the average mass, okay? All right, so again, a lot of review there. Hopefully you knew that already. Okay, in this last part, we're going to describe the difference between metals, nonmetals, and what we call metalloids. Sounds like a made-up word, but it's not. Sometimes metalloids are referred to as semi-metals. Okay, so it turns out that every element can be classified as one of those 3 things. So I'm going to first show you the metalloids, because it's easier to describe the other 2 if I start with those. There are a handful of elements that are considered metalloids, and I'm going to show you where they are on this table. You see the stair-step line that goes down here? That marks the locations of the metalloids. All right, so I'm going to put some circles around them. So boron, and then silicon and germanium. You see how we're kind of straddling the stair-step line? Now you'll find on different periodic tables that some elements and some are marked as metalloids and some on others are marked differently. When I look around the room, I can see different periodic tables and different versions will show different ones. And I will never make you memorize which ones they are. I just want you to know that they're near the stair-step line. Okay, so those circled ones are the ones that I'm going to say are the metalloids. Okay, so maybe write a note to yourself that you circled those. Okay, so all of the elements to the left of that, yes, we're writing right over top. Those are considered metals. And all of the ones these are the non-metals. It's a little difficult when you write over it. But so the vast majority of elements are metals. And then there's this handful of ones along the stair-step line that are metalloids. And then anything to the right of the stair-step line is considered a non-metal. So what do we mean by those? Now, I think you know some of the differences, but I'm going to describe in chemistry how we describe the difference. I think the one that you'll know best is just their appearance. Okay? So for the most part, and there's always a little bit of difference here from element to element, but at room temperature, most elements are hard, shiny solids. So think about the ones that are on there, and we can look at a few here. We've got copper and nickel. We've got zinc, gold, and silver, right? Magnesium, which you may not have seen before. Some of these are little metals that you get just from the foods that you eat, because your body needs a lot of these, what we call trace metals. There's the unusual one, mercury, the symbol Hg. Mercury is the only one that is a liquid at room temperature. So I might write here, mercury is liquid. And most of the nonmetals at room temperature are either gases or dull, brittle solids. So if they're solid at all, they're not things that, you know, are real hard and shiny. They might break on you. And if you think about some of the elements you know among the nonmetals, nitrogen and oxygen, right? Those are definitely gases because we breathe those things. Right? So what else can we say about these? Metals tend to be good conductors of heat and electricity. That means heat and electricity travel easily through conductors. Nonmetals are poor conductors. So if you want to make a wire, I would make it out of something like aluminum or copper, or the really high-end audiovisual equipment might have gold wires or gold contacts on it. Metals tend to have very high melting points. The temperature at which they'll melt, very high. It means you can get them really, really hot and they won't melt. That's good because like your car engine gets really, really hot. You don't want it to melt. Don't get it too hot. And these tend to have lower melting points. Metals tend to be shaped very easily. So there's two terms I want you to know. Metals are both ductile, sometimes called ductile, can be formed into wire. So ductile means able to be drawn out into a long wire, and also malleable. Hopefully you can see. If you're not watching on full screen, you probably should. Can be flattened. So it used to be when they would, before cars were made out of plastic, they were made out of metal, and they would have these what's called stamping factories, and they would just stamp into whatever shape they needed for that particular part of the car. Maybe the door, maybe the fender, maybe the trunk lid. Okay. And these can't be. So they are not ductile, they are not malleable. Okay. Don't ever try to make a wire out of something like silicon. Isn't going to work very well. Actually, silicon technically would be one of my circled ones. I guess that's a metalloid. But you couldn't do it out of phosphorus, or selenium is on there. You wouldn't even recognize most of those. All right, what's the last one? Generally, metals have 1 to 3 outer electrons. And remember, another name for outer electrons is valence electrons. Okay, so we see a lot of them here in group 1 and group 2. Those all have 1 and 2 outer electrons. Now, I know I haven't talked much about this big chunk here in the middle. Almost all of those have 1 and 2 as well. And then here's group 3. Okay, now there are a handful over here that kind of break the mold. Lead has 4. A few of the other ones, but those are pretty rare kinds of metals. And the nonmetals tend to have between 4 and 8 outer electrons. Again, these are general properties. Not every metal or every nonmetal will necessarily have exactly these properties. So those are the properties of metals and nonmetals. Well, what about properties of metalloids? I don't know if you'd know many of the metalloids. Silicon, you might see silicon sometime. Maybe I'll show you. I have a sample. But most of these are not ones you recognize. But I'm just going to summarize it as saying their properties are somewhere in between the metals and the nonmetals. So they're not going to be hard and shiny necessarily, but they're not going to be super brittle. They'll be kind of somewhere in between. They won't be really good conductors, but they won't be really poor conductors. They'll kind of be in between. So we'll just write it this way. Properties in between metals and nonmetals. So this kind of goes to show you what I said early on. When we have the arrangement of the periodic table, it's because the properties, the characteristics, are very similar among members of a group. So as we go over, we start changing some of those properties. By the time we're all the way over to the other groups over here, the properties have changed pretty significantly. Okay, so whereas sodium, if I put it in water, it would literally catch on fire and explode. But that will not happen with argon. Argon I can't even put in water. I guess I could. It's a gas. I could bubble into water, but nothing's going to happen. It reacts with absolutely nothing at all. Okay, which makes it very, very helpful for some things. Okay, so, all right. So that's the end of part 1. Have me take a look at this, get it recorded, and then we'll go on and we'll do a little something with this so you can learn it just a little bit better. Thanks for watching. Let me know if you have any questions.